All right, so we're going to shift now to talking about titrations. And we already know a good bit about titrations. We've done, countless titrations between Gen Chem 1 lab and what we've done in Chem 2 lab thus far. Let's just remind ourselves of the terms here, just so that we have clarity. So we know that titration as a process, this is where we're adding small amounts of one substance to another substance to try as best as we can to get the reaction to go to completion without going over. Um, and so the titrant is usually the substance that is in the burette. It's the one that we know the concentration of pretty well. The analyte would be the substance that we are titrating into. This is what is usually the unknown concentration substance. And then we have two terms here, the equivalence point and the end point. These two terms are very close to each other and are often used interchangeably, even though they are not actually interchangeable. Equivalence point is ultimately what we are striving for. The exact moment when the amount of one reactant and the other reactant have equaled each other out. We've gone fully to completion and there's no excess. That's what we ultimately are striving for with titrations. However, it's usually really difficult to get to that point. And the main reason it's hard to get to that point is ordinarily the solutions that we are using are clear and colorless. And when they react with each other, they produce clear and colorless solutions. And so, without any visual cues to tell us that the reaction is done or that the reaction is over, as in over titrated, we really don't have any good sense of where the equivalence point actually is. And so, one way that we get to estimate that equivalence point is using indicators. Indicators are organic dyes that will change colors at a certain pH, and that pH that we choose is the one that is pretty close to the equivalence point. And this gives us at least a rough estimate of where the equivalence point is, and we can use that to figure out the kinds of calculations that we were doing in Chem 105, where we were calculating concentrations or volumes or something along those lines. Well, we want to take a minute here and talk a little bit more about indicators. Indicators ultimately mark the endpoint because they change colors at and around that pH. Now, these indicators are usually organic dyes of some kind. They're organic acids or bases. And what we can see is that in those, if we look at the equilibrium of that organic dye, what we see is that for something like a weak acid indicator here, we would see that it would act as an acid and produce hydronium. And the fully molecular version in the reactants would be one color, and the deprotonated version in the products would be a different color. And so the key trick would be to figuring out when that transition takes place. Now, there are lots of different indicators out there. We've primarily focused on phenolphthalein, which we'll get into the reasons for that as we talk more about indicators and titrations. But generally speaking, we would like to see, for an indicator to be considered effective, the color transition that we want to see generally needs to occur within about 1 pH unit of the pKa for that indicator. So let's take a look at an example here. So here we have a titration, and we can see based on the starting pH and the ending pH, we've got an acid that we are titrating with base. And we can see that the equivalence point, which is, roughly in the middle of this part of the titration curve, pH point for that is about 7. And so we would want to choose an indicator that is going to change colors in and around pH of 7, preferably within, 1 pH point of that. And why is that okay? Well, because you can see how quickly the pH is changing here, and you can see how quickly or how not quickly the volume of sodium hydroxide is changing in that same region. So even if we don't pick an indicator that changes pH at exactly pH 7, we're generally okay if it does change colors near that pH. Because here at pH 8, we're relatively not that different from the volume of hydroxide at pH 7. And even here at pH 9 and pH 10, we're not that many volumetric units away. We're probably talking about hundreds of milliliters difference between them. So here are some common indicators that are used, and each of them have their own kind of capabilities and where we would find them most useful. Phenolphthalein, the one that we are most commonly familiar with, is right here. And we can see that phenolphthalein has a color range from about 6.5 to just about 11. But the color transition from colorless to that red, magenta, pink is starting to happen somewhere between pH 8 and 9. And so that's why we've been using it primarily. If we're doing a titration where the expected equivalence point is around pH of 7, yes, a phenol red might be a better indicator. Bromothymol blue might be a better indicator for that. But we do run into problems with those indicators in that we're going from one color to another. So there's going to be a transition point in between where there's a blend of colors. So for phenol red, the in-between state is yellow to orange to red. How do I know the transition between orange and red, or yellow to orange for that matter? As you might guess, the shades of difference are subtle. And same thing for bromothymol blue. We go from yellow to green to blue. The shading differences are going to be kind of tough there. Whereas going from colorless to pink, colorless to red, it's pretty easy to tell the difference between this has no color and this has some color. And so that's one of the reasons why we use phenolphthalein so often for those kinds of situations. It just is a better indicator because it's a much easier to see color transition. So let's answer this question together here. Is methyl red a suitable indicator for the kind of titration that we are doing in this graph here? And if it's not, let's go back to the previous slide and try to find a better one. So, first thoughts. Is methyl red a suitable indicator? Well, let's approach it this way. Is the color change in a part of the graph where we would be able to note its change without noting a significant difference in the amount of hydrochloric acid being added? I think we can all agree that the answer to that question is yes. Now, we can get into a different debate about the color change itself going from yellow to red at that, and when do we actually call it good? But at least from the standpoint of a pH perspective, yes, it's a reasonable kind of indicator. Would phenolphthalein be a reasonable indicator? Yeah, for some of the same reasons. Now, the color transition happening early as opposed to late, again, that's something that we would have to live with. That's the whole kind of problem with indicators in the first place. None of them are going to show the exact transition at the exact equivalence point. But does phenolphthalein have its full color change within that part of the graph that is, changing rapidly in pH without changing rapidly in the constant the amount of hydrochloric acid being added? The answer is there's yes. And so in both cases, we would say that these are suitable indicators for the transition. Which one would you take, one over the other? It's hard to say. I think both cases here you have a something that's prone to over titration just because if I'm titrating to the absence of color in the case of phenolphthalein, that can be a little bit difficult. But also if I'm trying to navigate that difference between yellow, orange, and red, that can be a little bit difficult as well. But both would have their strengths and weaknesses. You can make an argument for either one. So we want to move on to talking about these graphs, these titration curves. And what a titration curve is it's a graph where I'm looking at the pH on the vertical axis, the y-axis, compared to the amount of titrant added on the horizontal, the x-axis. Now, there are a variety of different titration curves that exist, and they fall mainly into three categories. We'll start with kind of the simplest one. This is a strong titration, meaning I've got a strong acid and a strong base, and I'm titrating them with each other. Well, if I'm starting with a strong acid in the flask and I'm adding sodium hydroxide base to it, this is the kind of curve that I would expect. And with this curve, I would expect a couple of things. First of all, I'm not going to see very much in the way of pH change until I get to the part that is near the equivalence point. And in this area where we have the pH rapidly changing in a strong kind of curve, what we're going to see is that that region is very fast and very large. So I'm going to see a rapid change in pH without a rapid change in volume added. So the rapid rise region of a strong curve, in this one, it's about 10 pH units. That's not necessarily going to be a consistent number that you see, but you are going to see definitely that there is a large period in terms of pH change without a whole lot of change in volume. Now, generally speaking, in the middle of that rapid rise region, that is where we find our equivalence point. So the equivalence point is at pH 7 in this particular case. And this is the point where we have equimolar amounts of sodium hydroxide and hydrochloric acid added to each other. And so since we have equimolar amounts, they cancel each other out perfectly. It's kind of that dream scenario of stoichiometry. There are no excess reactants. There are no limiting reactants. Everything has been done to the absolute perfection. That is the equivalence point. After the equivalence point, hydroxide starts to take over. We see another rapid rise region, and then the pH kind of levels off as the amount of hydroxide more or less just becomes saturated inside of that solution. So those are the highlights of a strong titration. Now let's talk about calculations. Since the reactions are strong, there's no equilibrium. And the reason there's no equilibrium is the strong acid and the strong base react with each other completely, and none of the conjugates are considerably strong or active toward water. All the conjugates are inert. So because of this, because there is no equilibrium associated with either of the acid or the base, calculations of this boil down to stoichiometry. And the way that we can figure kind of where we are in the graph, where we are in the plot, is we can start with how much hydrochloric acid was in the flask initially, how much sodium hydroxide have we added, how much is left over at the end. And if there's leftover hydronium, we immediately use that to calculate pH. If there's leftover hydroxide, we immediately use that to calculate pOH and then turn that into pH. But stoichiometry dominates these kinds of calculations. Now, if we titrate to the equivalence point, then this becomes just like any other problem that you saw in Chem 105. Titration equation, use that to figure out the concentration, use that to figure out the volume, whatever the case is. So here's an example problem. We've got 50 milliliters of 0.1 molar sodium hydroxide being titrated with 0.10 molar HCl. What is the pH of the solution after 10 mils of hydrochloric is added? So the way to calculate this is kind of similar to what we saw with the buffer problem when we were stressing the buffers. We can use a modified ice table to figure out what the final concentrations are going to be and use that to figure out what the pH is. So initially speaking, we have 10 milliliters of 0.1 molar. So 10 times 0.1, we have 1 millimole of hydrogen ion. 50 times 0.1 means we have 5.0 millimoles of hydroxide. And we don't care about the water. So we can tell immediately we're not at the equivalence point. Normal stoichiometry takes over. Limiting reactant tells us we're going to lose the smaller amount. So at the end of this, we'll have no hydronium. We'll have now 4.0 millimoles of hydroxide. And this is going to be distributed over 50 plus 10, that's 60 milliliters. 4 divided by 60 to two significant figures is 0.067. So that is the concentration of the hydroxide. So at the end of this part of the titration, we still have leftover hydroxide. Leftover hydroxide, we turn into POH, and we use that to figure out pH. So POH is equal to the opposite of the log of 0.067. Which would give a POH of 1.18. 14 minus 1.18 is 12.82. So with 0.1 molar sodium hydroxide, we would before the titration began, 0.1 would give us a POH of 1, and so a pH of 13. We've gone from pH 13 to pH 12.82. So we're still in that part of the graph that isn't changing considerably in pH. And the reason it's not changing considerably in pH is because, well, we've got lots of hydroxide present in this case. As we get closer to the equivalence point, we'll see that that number starts to kind of titrate downward, and then it'll just collapse. But this is how we handle, well, I mean, this is how we really handle any kind of titration calculation, to be honest. But for this particular type, because it's strong and strong, we don't have to worry about any kind of equilibrium in here at the same time. Questions with this example? All right, go ahead and try this one then. We've got a 20 milliliter sample of 0.2 molar hydrochloric being titrated with 0.2 molar potassium hydroxide. What is the pH after 15 milliliters of potassium hydroxide? Okay, so setup for this is very similar to the other ones. We're ultimately concerned with how many moles are present and how many moles are going to react. So we need to find millimoles of hydrogen. So that'd be 20 milliliters times 0.2 molar. So 4 millimoles of hydrogen ion. And for potassium hydroxide, 15 milliliters times 0.2 is 3 millimoles of hydroxide. Limiting reactant tells us we're going to lose 3 hydroxide and 3 hydrogen. So I'm going to have 1 millimole of hydrogen left, nothing left of the hydroxide, divided by 35 milliliters. So 1 divided by 35 is 0.029 molar. That's my concentration of hydrogen or hydronium ion. I can take the pH directly off of that. So the pH of 0.029 would be 1.54. Again, kind of in context here. In context, 0.2 molar HCl by itself would have a pH of roughly 0.7. So even at this later stage of the titration, we're getting very close to the equivalence point. We'd assume the equivalence point's about 20. But even here, we've gone from 0.7 to 1.5. We still haven't experienced a very significant difference in pH. Because ultimately, there's still quite a bit of hydronium H plus left in that solution, even after this much part of the titration has occurred. All right, any questions with this kind of calculation? This is some of the calculation stuff that you're going to see in the homework tonight with titrations. Is, just how do you calculate the pH at any different point in a titration? Okay, if we reverse the process, the titration curve does not change other than changing directions. Instead of starting low and going high, if we're starting with a strong base, we would start high and go low. But the idea would still be the same. We would have a large region where things are going to rapidly change. The middle of that region would still have an equivalence point at pH of 7. So strong acid, strong base, or strong base, strong acid, the titration curves have a lot in common. The only thing that is different about them is their directionality, which way they are going. Are they going up in pH or are they going down in pH? And so when we talk about titration curves, we tend to talk about titration curves in the idea of 4 stages. The initial stage, and so at the initial stage, we would be talking about, well, what is in the flask at that moment in time? And so if I have a strong base, then the thing that is in the flask at the beginning of the titration is just sodium hydroxide. And so I'd have sodium ions and I'd have hydroxide ions. And because I've got a high concentration of hydroxide ions, I'm going to see a really high pH as a result. The second phase of the titration would be the phase that is concerned with, okay, what's happening inside of that flask in the time between the start of the titration and the equivalence point. And what we see in that scenario is that not a whole lot is changing, other than, yes, some of the hydroxides are being converted to water, but I still have a reasonable concentration of hydroxide. And now I've got a couple of other ions in here as well. I've got chloride ions in here from the hydrochloric acid, in addition to the sodium ions that were already there from the sodium hydroxide. But since sodium chloride is a soluble salt, they stay exactly there. They don't combine and form a solid or do anything like that. They're just kind of floating there as spectators. At the equivalence point, we've added equal amounts of sodium hydroxide and hydrochloric acid. Notice what's left in this solution. No hydroxides, no hydroniums, just the conjugates. Water, sodium ions, chloride ions. Since sodium ions and chloride ions are inert toward water and won't react with it, this is how we know that we're at pH of 7. Because pure water has a pH of 7. And since neither of those ions react with water to move the pH up or down, it stays exactly there. It's at pH of 7. And then lastly, after we hit the equivalence point, now we start to see the presence of hydronium because the extra HCl is coming in. The H plus ion is reacting with the water to make hydronium. The hydronium ion is lowering the pH. And so once we get out of this region, we start to get into the acidic parts. We start to see that presence of hydronium there a lot more prominently. So those are the four regions, the four zones of a titration curve. And we can always talk about what is present at each of those regions for any titration. Now, again, if we were looking at the opposite titration, strong acid with strong base, basically we would have the same exact four pictures, just in reverse order. So if we're starting with hydrochloric acid and ending with sodium hydroxide, minus the sodium ions here, we would have hydronium at the start. Before the equivalence point, we would have a mixture of it would look a lot like this, except for some water molecules in there as well. At the equivalence point, it would look exactly the same. And then after the equivalence point, we would start to see the hydroxides come through. Now, when we get to weak acids and strong base titrations, this is the second kind of titration that we see, weak with strong. And when we have these weak, strong interactions, the titration curve has a lot of similarities to it, but there are some differences as well. So let's take a weak acid, strong base titration, for example, here. Couple of things that we would want to know. First of all, the equivalence point. Definitionally, it is the same thing. We have equal molar amounts of weak acid and the conjugate base. So we've added equal amounts of acid and base at that point. Stoichiometrically speaking, we are all kind of folded together. But there's one key difference. Let's take you back 2 slides here. In this reaction, we were able to say that we had a neutral pH of 7 because we had all water molecules, because all the hydrogens and hydroxides had reacted. But one different thing was that the chloride wouldn't react with the water, and neither would the sodium. If I'm titrating a weak acid, the conjugate base of that acid is not inert toward water. The conjugate base of that acid is reactive toward water. And so we're not going to get a pH of 7 because that conjugate base is going to react with the water, make an equilibrium with it, and put out a little bit of hydroxide in the process. So one key factor that we expect with these kinds of titrations, weak acid with strong base, is that our pH of the equivalence point is going to creep upward to a basic pH. How basic is the pH? Depends on the strength of that conjugate base. The stronger the conjugate base is, the more basic that pH is going to be. And so if we compare them side by side here, one thing that we will notice is that, again, the region here, the strong acid, strong base curve, we had this big call rapid rise region, we don't have that with a weak acid curve. The other thing that you'll notice, remember we kept commenting about how flat this region was down here, how the pH didn't seem to be changing a whole lot initially because we had so much hydronium or so much hydroxide still free in that solution. In the weak acid curve, we don't have that. And the main reason we don't have that is because here we're not seeing the overabundance of hydronium. What we're seeing here is the formation of a buffer. As we titrate strong base into that weak acid, the moment we start to add that strong base to the weak acid, we've started to create a buffer. And so what we're going to see with that buffer is we're going to see this gradual creeping up rise in pH as a result. Now, one key attribute to that is that if we can identify where the equivalence point is, at the half equivalence point, halfway between 0 and the equivalence point, we would have in that spot the formation of what we would call a perfect buffer, where we have equal molar amounts of the two conjugates. At that half equivalence point, the pH and the pKa for the acid are the same. Where this can be especially useful for us is if we have an unknown acid and we cannot identify what that acid is based off of reactivity, we can do the titration and compare the pKa of the acid that we determine experimentally with the pKa's of different acids that we know and try to match them up. So the four regions in a weak acid strong base titration are similar yet different to what we were talking about with the strong. For the first one, we can definitely determine the pH of that weak acid. Only difference is we have to do it by using weak acid equilibrium Ka as opposed to just calculating the number of millimoles, the concentration of the hydronium. In that range between the initial and the equivalence point, we have the buffering region. And so we can use the Henderson-Hasselbalch equation to calculate pH. A keynote of that point is that halfway into that region, pH and pKa are the same thing. At the equivalence point itself, we're going to have pH greater than 7 due to the presence of the weak base. We can find the pH in that region by using the Kb of that conjugate. Once we cross over that equivalence point, then it just becomes a matter of we have excess hydroxide. We can use the excess hydroxide to calculate the pH. So in titrations involving weak acids or weak bases for that matter, in those kinds of titrations, what we'll see is that the calculations that we do are essentially the same kinds of calculations that we have been doing all along. We just have to know which one to use when. We have to know what part of the titration curve that we are in. And so let's end today with a pair of top hat questions. So first question, can we identify where the half equivalence point would be on this graph? And so the answer to that question, at what volume is the equivalence point? It's at 50. Okay, so if the equivalence point is 50 milliliters, the half equivalence point would be half of that volume. So we should be looking here at 25. All right, and this is where we're going to stop for today.